Okay, we are now registering. Let me share screen. Perché ho fatto questo qui? Non l'abbiamo capito. Boh. Okay, do you all see the slide?
Yes. Yes.
Okay. So, okay, let's start. Okay, the microphone. All right. So, as you can see, today we start the second module of the course. This module will take us 3-4 lessons. It is quite important because it provides some basic but fundamental theoretical ingredients that we will be using all over the course, actually, to construct the rest of the course upon this. Okay. So in this first part, we'll talk today about transition probabilities, cross-section, and decay rates. Okay, I guess part of these arguments you already know from previous studies, but maybe you will learn something new today. So, so in general particle physics, this is essentially with two types of processes, collisions and decays. But in both cases, one needs to calculate the transition probabilities between initial and final quantum states. Now, what will follow now is a pure non-relativistic quantum mechanical treatment, okay, that you find in any textbook of quantum mechanics. It is just based on the Born approximation and on perturbation theory. So all these you find in any textbook of quantum mechanics, and I guess you already have studied in previous studies. So I will not go into the details. I will not develop all the algebra. So the aim here is just to make the main ideas and to try to make the logic that bring us to the derivation of the famous Fermi golden rule. Okay. So let me start. So let's consider a physical state, which is described at a time t smaller than t0 by this initial state wave function, psi I, okay, where this exponential here gives the normal time dependence of the wave function, and phi I is the eigenfunction of the unperturbed Hamiltonian H0, corresponding to an energy eigenvalue EI. So you see here the eigenvalue equation for the unperturbed Hamiltonian. Phi I is our eigenstate, and EI are the energy eigenvalues. Okay, and this eigenstate in the Born approximation, which is the approximation we will be using in this treatment, is just a simple plane wave. So we don't have any interaction, and so the simplest wave function one can think of is just a plane wave. Okay. Now, suppose that at a certain time t equal to 0, an interaction potential starts to be effective. Now the total Hamiltonian becomes the sum of the unperturbed Hamiltonian plus an additional term, which is an interaction term, okay, which we can express in terms of the potential energy or even in terms of the potential through some coupling constant that we call G0. For instance, for the case of electromagnetic interaction, this coupling constant is simply the electric charge, okay? So the physical meaning of this constant depends on the potential you are using. So this, so far we are very general. So now, as a consequence, for time later than t0, so when this potential is effective, the wave function must satisfy the time-dependent Schrödinger equation with a full Hamiltonian, so both the unperturbed part and the interaction term, so the potential energy term. And so the final state, so the wave function can be expressed as a superposition of the complete set of possible final states, as you see here. Okay, so these are now the final states. Suppose there are n different final states, all possible, okay, or orthogonal. And this coefficient here, which is time dependent, as you can see, represents the probability amplitude to find the system in a given state phi k. Okay, and then you sum all of them. So you essentially calculate the superposition of all these possible final states. Now, clearly, at the beginning, so before the interaction becomes effective, when there is no interaction, essentially, one must have that this probability amplitude must be 1 for the initial state and 0 for all the final states, of course. Okay. But what happened when we have now the interaction? So in perturbation theory, as you know, it is assumed that the potential U is sufficiently weak that it can be treated as a small perturbation. And therefore, the transition probabilities are very small at any time t greater than 0. So still, at time t greater than 0, one still has that the probability to that the quantum state is still the initial state is almost 1, okay? And there is a non-zero but very small probability that the system is found in some of the final states. Ok? Tutto chiaro, ragazzi, fin qui? Is all clear? I guess you know all of this.
Yes.
Okay. Now, let's consider one possible final state. So we call this psi f, okay, which is usually in the form of a plane wave. Now, we construct the transition probability amplitude in this way, okay? So as a matrix element of the energy potential between the initial and the final state. And this we can write either in the bracket notation or equivalently in the integral notation, okay? Where this is the complex conjugate of the final state wave function. And the integral is over the volume, okay? Now, it turns out, this we will not derive, but you can find in textbooks, quantum mechanics textbooks, that the probability amplitude, Cf, to find the system in this final state psi f, is given by the Fourier transform of this transition probability amplitude. So it is defined in this way. Okay? With the time running from t0 to a certain time t, where this quantity is calculated. And considering now all possible final state, one can define the total transition probability per unit time. So this is what we call the transition probability rate, which is given indeed by the sum of the probability of all possible final states divided by time. And so this 1 over t tells you that this is actually a rate, okay? A transition probability rate in unit of times. Now here we have a sum over the n possible discrete quantum states, okay, final quantum states. But of course, since in both collisions and decays, the final state particle can occupy an energetic level, any energetic level allowed by energy conservation, the sum over all possible discrete quantum state, so this sum here, can be replaced by an integral over all possible energy state in the final channel, okay? So we are now making this transition from the discrete sum over final quantum state to an integral over all possible final energy states, okay? Of course, we maintain here the square of the transition probability amplitude, okay? Now, we can replace here the expression of this coefficient, okay, which is given in terms of the Fourier transform of the transition probability amplitude, TFI, okay? And we can define here this rho as dn over df, which is called the density of final states. And this represents the number of final states which are available per unit interval of energy. Okay? Now, once we solve this integral, we will not do here the algebra, of course, but once this integral is solved, you obtain the final expression for this transition probability rate, okay, which is given in the form of the famous Fermi golden rule that I'm sure you already know from past studies. So we have a constant here, then we have the square of the transition probability amplitude, and we have the density of final states. Okay. So indeed, apart from the constant, we have two main ingredients here. The transition probability amplitude, which describes the physics of the process. So the dynamics of the process is included here. The dynamics of the reaction we are studying is all included here. And the density of final states only describe, let's say, the kinematics of the process, or if you like, the phase space of the process, okay? So we have the dynamics inside here and the kinematics right here. Okay? Now, at first order, in perturbation theory, the transition probability amplitude is given in the form that I just showed before. okay? But of course, one can make an expansion in perturbation theory, so considering also the second order, the third order, etc. So if we consider also the second order, okay, then we have an additional term here to be considered. So the first term represents the usual scattering in a potential, the potential U, which is related to this potential energy V through the coupling constant. And now the second term represents the transition occurring via some intermediate state K. You see here that the intermediate state K is entering the expression here. And of course, we can have here, in principle, infinite higher order terms in this expansion, okay? Of course, in perturbation theory, as the name says already, the interaction is only a perturbation, okay? So all the higher order terms are absolutely negligible, and one can obtain already a very accurate prediction by only considering the very first terms in this expansion, okay? Let's now derive the full expression of the density of final states, okay? Now, so suppose we have a reaction, okay, so we have two final state, two initial state particles that interact, and then after the reaction we have some final state objects, okay? And in particular, consider a particle which is scattered or decayed, this also applies to decay, of course, over a spatial volume V spatial, and in the momentum interval from PF to PF plus dPF. So we consider in a final state as in the volume in spatial coordinates, VSP, okay, and also an interval in the final momentum from PF to PF plus dPF, okay, an infinitesimal interval in final momentum. Now, if you work now in the momentum space, this infinitesimal interval corresponds to the volume of a spherical shell, okay, with inner radius PF and thickness dPF. Okay, I think you know this already from the past. And so essentially, the volume, the infinitesimal volume in the momentum space, the Vp, is given by the volume of this spherical shell, which is nothing else than 4 pi p squared dp. Okay, so we have now a spatial volume in the coordinate space and a momentum volume. And altogether, when you combine the two, you get the total volume in the phase space. Now, there is another important ingredient that we have to use here. It is the following. So according to the uncertainty principle, in non-relativistic quantum mechanics, each state or each particle occupies a volume in the phase space which is equal to h to the cube, where h is the Planck constant. And so this you can also write as in terms of h bar, okay, if you like, that's 2 pi h bar all to the cube. So again, this is the elementary volume in the phase space. So the volume occupied by one single state in the phase space. And now we have all the ingredients to write down the form, the expression of the density of final state, okay? So by definition, rho is dn over df, where the small f stands for final state, of course. So dn, okay, the, let's say, number of final state in this infinitesimal phase space volume is given by the total infinitesimal phase space volume, which is the product of the spatial volume times the infinitesimal momentum volume, divided by the volume occupied by one single state, which is this h cube, okay? So once you take this ratio, you get dn. And then you are still left with 1 over def. Now, we can put the full expression of this infinitesimal momentum volume, okay, which is the volume of the shell. So we can write down this explicitly. And we can use some very simple classical arguments to derive the expression of dp over de. Okay, so in classical mechanics, as you know, p is the momentum, e is the kinetic energy, so you can differentiate both. And when you take the ratio, you just find that it is the inverse of the velocity. Okay, so we can just substitute this dp over de as 1 over vf, where vf is the velocity of the final state particle. Okay. If I'm going too fast, please stop me or slow me down. Okay, I assume that you know most of these things, so I'm going fast. But if it is too fast, just let me tell you, and I will repeat slower. Okay. Now, so the expression that we got now for the energy of final states is this one. Okay, after implementing these. So we are simplifying here some constant. So at the end, we get this. No, everything is here, right? So what is important to note here? It is important to note that it depends on the square of the final state momentum. Therefore, a final state with lighter particles, which will be produced with larger momentum, are kinematically favored over final state with heavier particles. So in other words, if in your reaction you produce light particles, this by momentum conservation, they will have a higher momentum, okay? And so since this enters as a square in the density of final state, you will have a much wider phase space available for your reaction. If, on the other hand, you produce heavy particles, by energy momentum conservation, they will have only a small momentum, okay? And so also the phase space available for your reaction will be small, okay? And this dependency is quadratic. And then I also put this spatial volume in red because we will come back to this in a few slides. So we still have a dependence on this spatial volume that we want to drop. All right. Now there is a quite important feature of this discussion, which is about the normalization of the wave function, which becomes to be quite relevant when we will move now to the relativistic discussion with Lorenz invariant wave functions. So let me start from the non-relativistic case, okay? So as you know, to ensure a correct volume integration for the transition probability amplitude, the initial and final state wave function need to be properly normalized. So we have to put here some normalization coefficient on top of everything, okay? And how is this normalization coefficient defined in non-relativistic quantum mechanics? So in non-relativistic quantum mechanics, each wave function is typically normalized to one particle in a cubic volume of side L. Or in other words, one imposes that a particle has a probability 1 to be found inside a cubic box of side L. Okay, so this is the way one imposes the normalization of wave function, typically in non-relativistic quantum mechanics. So when we impose this condition here, so we impose that the probability to find our particle inside this cubic volume is 1, okay, and we put our normalization coefficient in top of our wave function, we obtain something like a squared times L cube equal 1, where L cube is the volume, the spatial volume, okay? And so we can invert this and find out that a squared is the inverse of the spatial volume, and so we take the square root. So this normalization coefficient in quantum mechanics is typically the inverse of the square root of the spatial volume. Okay. Now this now becomes relevant because the calculation of the transition probability rate must not depend on the normalization volume. Okay, this is an arbitrary choice, of course. And in fact, the volume dependence in the expression of rho, the one that I put in red before, let me go back here, so this guy here, at the end, cancels with the inverse of the spatial volume, which is associated with the wave function normalization that enters the transition probability amplitude. Okay, so at the end, we will cancel the dependence on the spatial volume. Okay, due to this properly defined wave function normalization. And so, since the volume will not appear in the final result, it is convenient to set it equal to 1, which corresponds to normalize to 1 particle per unit volume, okay? So whatever number you put here, it is irrelevant, because at the end, the final result, the volume dependence will cancel out. So once we do so, our density of final state will reduce to this expression here. Okay, we still have the square, the momentum, the inverse of the velocity, and all the rest is constants. So far, we neglect completely the spin degrees of freedom of our particle. So let's now suppose that we also have spin to take into account. So suppose we have a reaction like this, E plus B that goes into C plus D, okay? And suppose that the final state particle, C and D, have a non-zero spin that we call SC and SD, okay? Then the number of available state in the final state of available final states is increased by the multiplicity of the spin states. Okay, so if these objects come with some spin, either integer or alpha integer, we have to increase the number of final states by the multiplicity of the spin states, which is given, as you know, by 2SC plus 1 times 2SD plus 1. Okay, so we have to include this factor to be more general, into the expression of the final, the density of final state. Okay, and once we do so, we put it here in the numerator, we obtain now the full expression of the Fermi golden rule. Okay, so again, the Fermi golden rule has two main ingredients: the square of the transition probability amplitude, which contains all the physics of our reaction or our decay. So all the dynamics is inside here, because here this contains the potential. Okay, and all the rest is kinematics, or if you like, phase space. Also properly accounting for the multiplicity of spin states. Ok? Tutto chiaro ragazzi fin qui? Is all clear?
Sì, prof.
Ok. Ripeto, sono andato un po' veloce perché penso che queste cose qui le conosciate già, o comunque sono concetti che maneggiate abbastanza bene. Now, so far this was non-relativistic. Of course, as we discussed in the previous two lessons, we are interested in a relativistic treatment for particle physics. Okay, so we want to make all these arguments Lorenz invariant. Okay, and now we have a problem to solve. Okay, and the wave function. The point is that the wave function normalization of one particle per unit volume is not Lorenz invariant, and the reason is pretty obvious, because suppose you have you want to evaluate this volume in a boosted reference frame, so after Lorenz transformation, then, of course, the original normalization volume will be Lorenz contracted in the direction of motion by a factor 1 over gamma. The Lorenz contraction that we discussed in the first lesson, if you remember, with also the problem of the muons, the cosmic muons. Okay, so the initial volume in this original frame is L cube, but now in this boosted frame is L times L times L divided by gamma, because it is Lorenz contracted in the direction of motion, which is this one here. Okay, so the total volume is now not anymore L cube, but L gamma, and so it's not universal. Okay, it changes if you change a reference frame, so it is not Lorenz invariant. Okay, and this we don't like, of course. Now, if you remember, we can also invert the expression of the total energy. Okay, so 1 over gamma is also essentially 1 over the total energy. So this is proportional to L cube divided by energy. So how can we solve this? So since the boosted volume is a factor of gamma smaller than the original one, the original normalization of one particle per unit volume corresponds to a normalization of gamma particles per unit volume, or equivalent of E particles per unit volume in the boosted frame. Okay, essentially, suppose you have the same number of particles here and there, but now your volume is squeezed, so you have a larger density. Okay, so it is like in the original volume, you don't have one particle, but you have gamma particles. Okay, to get the same density. So this is clearly not Lorenz invariant. So a Lorenz invariant wave function normalization must therefore be proportional to E particle per unit volume, okay, such to compensate the effect of the Lorenz contraction. Okay, so here the volume is essentially a factor of E smaller, but if we multiply by E, okay, we cancel this effect and we obtain again a volume which is universal. Okay. So the idea is that to get a Lorenz invariant wave function normalization, one should divide by E, one should normalize by E, okay? But then for historical reasons, this is done actually by twice E. Don't tell me why, but this is the way it was introduced in the past. So this is now the proper Lorenz invariant wave function normalization, okay, with square root of 2E. And so when you calculate these overall the full volume, you get 2E as a result. This is the way wave functions are normalized in a Lorenz invariant way. Okay. Now, let's stop here for now, and we will come back to this in a few minutes, but let me, first of all, introduce the concept of cross-section that you already know, of course, but let's introduce from scratch. So let's consider a fixed target reaction, E plus B, that goes into C plus D, okay? And we define the flux, the number of incident particles per unit time and unit area, okay? The number of beam per unit time, second, and unit area, square centimeter. Now we can make the trick of multiplying and dividing by centimeter, so by the length. And so what we get here is now the number of beam particles per volume, so the density, the spatial density of beam particles. And what we get here is a length over time is the velocity of the initial particles. So we can always express the incident flux, so the flux of the beam particles, as the volume density of the beam particles times their velocity. Now, suppose now we want to study this reaction here, A plus B that goes into C plus D, and it is, of course, intuitive that the number of interactions per unit time, so the interaction rate, between the beam particles of type A and the target particles of type B must be proportional to both the incident flux, of course, but also to the total number of target particles in the given volume. Okay? So the higher the incident flux, the higher your interaction rate, but also the higher the number of target particles, the higher your interaction rate. So clearly the rate must be proportional to the product of the incident flux and the number of particles NB, where the number of particles is given by the density of target particle times the volume, of course, by definition. Okay. So here we have a sign of proportionality, but we can make this as an equation if we introduce a proper proportionality coefficient that we call total cross-section. Okay, so the rate is given by the total cross-section times the incident flux times the number of target particles. This total cross-section must have the dimension of an area, so we measure it in square centimeter, or as you know, in bar, or microbar, nanobar, picobar, whatever. Okay. And so we can invert this, and so we can express the total cross-section as the number of interactions per unit time and per target particle, divided by the incident flux. So in the denominator, we have the incident flux, phi A, that we can write as NA times VI. In the numerator, we have the number of interactions per unit time and per target particle. So it is the rate divided by the number of target particles, which is nothing else than our beloved transition probability rate, W, that we defined before, the one given by the Fermi golden rule. Okay, so we can now substitute this here and find out the expression of the cross-section for the non-relativistic case. So let me do this on the blackboard. So I have to switch. Ok. Da casa vedete la lavagna?
Sì, sì.
Okay. Okay. Speriamo che oggi i pennarelli vanno bene. In ogni caso ne ho portato un po' dei miei.
Prof, solo l'angolo in alto a sinistra si vede un po' poco, però...
Allora, quest'angolo qui non si vede?
No, no, si vede ancora, quindi va benissimo.
Ah, ok. Vabbè. Okay. So our total cross-section, sigma dot, is, as we found, is given by the transition probability rate divided by the incident flux. So NA times PI. Riuscite a vedere bene, ragazzi?
Sì, sì.
Perfetto. So now let's substitute here the Fermi golden rule. So this is 1 over NA times PI. Then we have the constant 2 pi divided by h bar. Then we have our squared transition probability amplitude. And then we have the density of final state, so N over dEF. Now we need to put here the full expression of the density of final state. So this is going to be equal to 2 pi divided by h bar. Then we have the square of the transition probability amplitude. And now we put the full expression that we derived before for the density of final state. So we have the spin state multiplicity, GF. Then we have 4 pi. Then we have the momentum squared. And here we have NA, VI, VF and then the elementary phase space volume. Okay. Now let me write this in a more useful way. So we put all the constants here. So it's 2 pi squared h to the 4th power. We are doing some simple algebra here. The square transition amplitude. And then we have gf times bf squared divided by di times bf. Then we have 1 over NA. And then we have this 4 pi. So the meaning of this 4 pi is actually, as you might already infer, is the full solid angle. Okay. And I will try to convince you about this. So let's consider a fixed target experiment. So this is our incident beam particle. Then we have a fixed target here. Okay. And then we want to study this reaction in the volume. In particular, we want to look at the particles which are emitted in an infinitesimal solid angle. It is the omega, okay, which corresponds to a surface, an infinitesimal surface that we call a dA, at a distance r from the interaction point. And by definition, as you know, the infinitesimal solid angle is given by the infinitesimal surface divided by the distance squared. Okay. And if we now write this in spherical coordinates, this is nothing else than r squared sine theta, the phi, divided by r squared. And so we can also simplify this one. And we can integrate this element of the element of solid angle in the full volume. So omega is given by the integral of the omega. We use spherical coordinates, so this is the integral over from 0 to pi of sine theta the theta, and then the integral from 0 to 2 pi in the phi. So we are integrating what remains here, so this part here. So this is very trivial. So the second integral is just 2 pi, because we don't have a specific dependence on the phi. Then we have the minus cosine theta from 0 to pi, which is again 2 pi. Cosine theta from pi to 0. It is 2 pi that multiplies 1 minus 1. So overall, we get our 4 pi. So let's consider the case of one single beam particle. So Na is equal to 1. Okay. In this case, the total cross section will look like sigma top is equal to 1 divided by 2 pi squared, h bar to the 4th. Then we have our transition probability amplitude squared. Then we have all our friends, df, bf squared divided by vi, vf, and omega. Okay, let's come back to the slides. Other sharing. Okay. Ok, vedete le slide di nuovo? Da casa vedete le slide?
Sì, sì,
Okay.
sì.
Allora, sono costretto a fare questo giochetto ogni volta, perché l'altra volta non l'ho fatto, ma poi nella registrazione la lavagna non si vedeva più. Quindi ricordiamoci di fare questo switch ogni volta che passo dalla lavagna alle slide. Ok, so now we're here. So let me just copy on the slide the expression that we just draw on the blackboard. Actually, this is the differential cross-section. So now we take the differential over the solid angle for a single incident particle, okay? And with the scattered particle emitted in an infinitesimal solid angle d omega. So this is the expression that we got. Now, let's make some considerations here, okay? So one can play with this formula in two directions. By measuring experimentally, okay, the cross-section, this relation allows to obtain information about the transition probability amplitude, okay? So you measure these, you infer about T phi. And why is this important? Because, as I told you, this matrix element contains all the information on the physics, on the dynamics of the process, because it includes the potential, okay? And this is, for instance, a very useful approach for instance, the strong interactions where the potential is not known in the non-perturbative regime, as we will study next, okay? But one can use this also in the opposite direction, okay? Suppose that your theory is extremely precise, as the quantum electrodynamics, as we will study in the next weeks, okay? Then you know perfectly your potential. You can calculate extremely precisely your transition probability maximum, and so you can make prediction to the cross-section to be compared with experimental values, okay? So you can play around in two directions here. Now, a few other considerations. The total cross-section in general is given by the sum of the elastic and the inelastic cross-section. Elastic means that the final state particles are the same as the initial state. Inelastic, this is not the case anymore, so you can have different or more particles in the final state, or excited particles in the final state. Another important consideration is that the derivation of the Fermi golden rule that we give today is based on non-relativistic quantum mechanics, okay? And therefore, the resulting cross-section that you see here on top is not Lorenz invariant. Okay, it works well, of course, for low energy phenomena, where you don't need to be relativistic, but if you want to describe relativistic phenomena with this cross-section, you will fail, okay? So what we need now is to derive the Lorenz invariant expression of the cross-section, okay? Such that we can use it in high energy phenomena. And let me go back to what we learned before about the Lorenz invariant wave function normalization. So now we will make use of this result. So neglecting for the moment the spin degrees of freedom, the Lorenz invariant expression of the total differential cross-section for a generic two-body reaction, A plus B that goes into C plus D, we will use natural units for simplicity, is given by this expression here, okay? So, of course, the expression is different than the non-relativistic one, but the main ingredients are still there. So we still have a square of a transition amplitude, we still have the density of final state, and we have some normalization constant, okay? Now, the main difference, indeed, is in the wave function normalization constant. So we now have these twice energy for the initial state particles, and also the Lorenz invariant transition probability amplitude, MFI, is related to the classical one through these proper wave function normalization coefficients. Okay. What about now the density of final state? Okay, so we can write now the expression of the differential Lorenz invariant density of final state, and this looks quite complicated, but in practice there's nothing special here. So the delta function ensures form momentum conservation. So the final form momentum must be the same as the initial form momentum. Okay, this is the only case where the delta works. And these two objects here are now the elements of Lorenz invariant phase space. So in the, let's say, classical non-relativistic quantum mechanics, this was essentially h to the cube, okay? In a Lorenz invariant description, this is given by these terms here, for each of the final state particles. So if you have a simple reaction such as this one, C plus D, then you're going to have one for the C particle and one for the D particle. In general, if you have n final state particles, you have to take the product of all these terms. Okay, all these will contribute to your infinitesimal phase space. And now we can integrate, so we can get now the Lorentz invariant expression for the total cross-section. Okay, so we put the constant outside, and then we integrate over all the energy and momenta of the final state particles, and of course our transition probability amplitude is inside the integral n squared as usual. And this can be further generalized in case of n particle in the final state. So suppose your reaction, you have C1, C2, Cn, then you have to take the product of all of them rather than just two, in this simple case, and also inside the delta function. Okay, so you take the product of the momenta of the final state moment, and then you substitute here and subtract those in the initial state. Okay, now, what means Lorentz invariant? Lorentz invariant means, by definition, that it is universal for all reference frames. Okay, and in fact, this is the case. And so the most convenient choice is to work in the center of mass frame. Okay, where we know that the center of mass energy is the sum of the center of mass energies of our incident particle or final state particle. We know, as we have seen last week, that the total momentum must be 0. And so the momenta in moduli must be the same in the center of mass. That for the initial state we call pi star, and for the final state we call pf star. Okay, and so in the center of mass, the shape of the cross-section, this is the differential cross-section, is this one. Okay, so we have S, which is the Mandelstam variable that we studied last week. We have the ratio of the final to initial momentum in the center of mass, and as usual, we have the square of the transition matrix. And then we can integrate these over the solid angle to get the total cross-section. Okay. Now, so far so good, but we didn't take into account the spin degrees of freedom. So now we want also to include this possibility. So if neither the beam nor the target particle are polarized, the spin of the final state particle are not, and the spin of the final state particle are not measured, we must sum over the final spin states and average over the initial one. So what does it mean? Suppose you are studying your reaction, A plus B that goes into C plus D, okay? Then suppose that your beam and target particle are not polarized. This means that the spin direction is random, okay? They are not all aligned in a preferred direction. So if this is the case, then of course your reaction is not polarized because your incident and target particle are not polarized. The same thing happens in the final state. So you get, for instance, the C and the D particles, okay? And then if you don't measure their polarization, that means that you are essentially summing over all possible polarization states. So in order to take all these into account, the prescription is to average, to average over the initial spin state and to sum over the final spin state. So to make this in formula, averaging over the initial state means summing over the initial state and divided by the number, which is given by the spin multiplicity that we discussed before. So we sum over the initial state and divide by the total number, okay? And this is the average of the initial state. And then we have also to sum over the final state spin. And all these objects here can be written in a much more compact way, okay? In terms of this spin averaged transition matrix element squared, okay? So at the end, this is the expression of the cross-section where we are not taking into account the spin degrees of freedom of the initial and final state, or to be more precise, where we are essentially averaging over all possible spin states. Okay, so keep this in mind because we will make use of this formula next in the course. Okay, let's make a break, maybe 5 minutes break. If you have questions, otherwise we recombine at 10:10, okay? 10 past 10. Okay. Okay, we can restart. So let me share again the window. Ok, vedete le slide da casa?
Sì, sì.
Ok, allora riprendiamo adesso. So, so far this was about cross-section of reactions. Let's now treat the case of decays, okay? Of course, we have a parallel treatment for decays, but the reasoning is quite similar. So, in general, what is the mean life or the decay time, okay, of an unstable particle? So, it is defined in the center of mass system of the decaying particle when the particle is, of course, at rest. Okay? It is specific of each particle. Each particle has a different mean life, of course, and corresponds to the time needed to have about 2/3 of the original particles decayed. So let me show very briefly these on the blackboard. So we make use of the standard exponential rule for decays. So we know that the number of survived particles at the time t is equal to the total number, and 0, times e to the minus t over tau, where tau is the mean life of the particle. Okay. Now, the meaning of tau is that when t is exactly equal to tau, then we're going to have n tau equal to n0 e to the minus 1. That is n0 over e, which is about 0.37 times n0. So this is the number of particles that survived. So the number of decayed particles at the time t equal tau is going to be the total number minus those that survived, so minus n tau. So this is n0, 1 minus 1 over e. That is about 2/3 of n0. Okay, this was absolutely trivial. Let's go back to the slide. Okay. Now, the mean life tau can vary from essentially infinity for stable particles, and to our present knowledge, for instance, the protons and electrons are stable particles, to something like 900 seconds for the case of neutron. You know that neutron decays spontaneously into proton through the beta decay, as we will study, but also down to 10 to the minus 24 or even 25 for hadrons or very unstable heavy particles. Okay. Now, for a decaying particle, the transition probability rate is simply given by the inverse of the mean life. Okay, it is a rate, so also dimensionally it is consistent. The higher the decay transition probability rate, the smaller the mean life, and vice versa, of course. Now, as we will study next in the course, hadrons, subject to the strong decays, appear in experiment as wide resonances that we call hadronic resonance. So essentially what you have here is that the value of your cross-section as a function of the energy, center of mass energy, okay? And so suppose that experimentally you are able to tune your accelerator and so to change the energy step by step, you will find that in correspondence of some hadrons masses, you find that the cross-section get a steep peak like this one, okay? Which is centered indeed at the mass of the resonance. And one can also measure the width of this resonance, in particular the full width at half maximum. Okay. Now, of course, we will come back to these several times during the course, so don't be scared. Let's now just make some simple arguments. So we apply the uncertainty principle for energy and time. So we replace the uncertainty on the energy as half the width at half maximum, so gamma squared, gamma divided by 2, sorry. As a time, we take the mean life, and this must be of the order of h bar divided by 2. So This turns out to be gamma tau equal to h bar, and so we can invert this and write down that the decay width, okay, this guy here, is inversely proportional to the mean life, and it is actually proportional to the Planck constant to the transition probability rate as a consequence. So a few considerations. The higher the transition probability rate, W, the greater the decay width, gamma, and the shorter the mean life, tau, of course. The decay width provides the transition probability per unit time for decay processes. So in other words, the decay rate that we said before. Therefore, by measuring the decay width, gamma, okay, experimentally, so by measuring the thickness of this resonance, one can infer the decay probability W and the interaction potential that is, of course, defined inside here. And of course, the decay width gamma that we introduce here for the hadronic resonances is a more general concept, and it is also used for electromagnetic and weak decays, as we will study.
Sorry, Prof.
Yes.
What do you call hadronic resonances?
Okay, I will explain again. So, as we will study next in the course, from the experimental point of view, when you make a high energy reaction, for instance, and you produce hadrons in the final state, unstable hadrons, I mean, okay, these hadrons decays in a very, very, very short time of the order of 10 to the minus 24 seconds, if the decay is regulated by the strong interaction. All this we will study next, so don't worry, okay? So from the experimental point of view, you are not able to measure such short times. No any particle detector can give you a measurement of such a short times. The only thing you can measure is actually the inverse, so the decay width. So you tune your machine, you change step by step the energy of your machine, your accelerator, okay? So essentially you measure step by step the cross-section at different values of the center of mass energy. And sometimes you find that your cross-section rises like a peak and then goes down. And the value of the maximum corresponds to the mass of your hadron. Okay, and the decay, the width of this hadronic resonance, okay, is inversely proportional to the decay width, to the decay time, sorry, or to the mean life. Is any more clear, maybe?
Yes, thank you.
Okay. Anyway, we will study this in detail also from the formal point of view, so we will come back to hadronic resonances several times during the course. Now, in general, a particle can have different decay modes with different probabilities, of course. Okay, and each mode is characterized by a specific branching ratio. So the branching ratio is the probability of decaying in one single mode, in one specific mode I, divided by the total decay width. So this is the partial decay width divided by the total decay width. Of course, the total decay width is the sum of all the partial decay widths, and the sum of the ratio, by definition, is 1. Let's take as an example the charged pions, okay, that we already encountered in some problems last time. So this is the pi plus and pi minus. The mass is of the order 140 MeV. The lifetime of pions is relatively long, okay, is 2.6 10 to the minus 8, which is immensely longer than these 10 to the minus 24 that you have for heavy hadrons, of course, okay. Now, in the last column, you see all the possible decay modes of the pions. So the pion can decay in muon and neutrino, electron neutrino, etc., etc. And in the last column, you find the branching ratios. So the probability for each of these specific decay modes. So for instance, what you see here is that the decay mode in muon and muon neutrino is by far the most preferable, okay, most probable. And then we have also, with very tiny probabilities, other possible decay modes. Now, let me ask a question to all of you. So just by looking at this table, can you infer which fundamental interaction regulates the decay of pions, charged pions?
Weak.
Yes. Why?
Because we've got leptons coming out. We had in decays into leptons mostly. That's what I mean.
Yeah, and more specifically, you see neutrinos, and neutrinos are everywhere. Neutrinos can only feel the weak interactions. Okay, so this was indeed a comment here. Okay. So in fact, yeah, that was the correct answer. So the pions, which are the lightest hadrons, can only decay through the weak interaction, okay, for the reason that we will understand later in the course, of course. Okay. This is, whereas heavier other particles can decay to the strong interaction, to the electromagnetic, or to the weak. For instance, the neutral pions, the pi0 that we also encountered last time in some exercise, they decay electromagnetically through, if you remember, 2 photons, pi0 into gamma gamma. We studied in the two-body decay problem, if you remember. Now, so let's write down the Lorentz invariant differential decay rate for a particle A decaying into, in general, n particles. So, as usual, we have our squared matrix element, which contains the dynamics of the decay and the interaction that regulates the decay. We have the proper wave function normalization. We have the elementary phase space volumes, Lorentz invariant, okay, the way we define. We have the delta Dirac, which ensures for momentum conservation in the process. The integrated decay rate for the case of two-body decay is now given here, okay? So we are now integrating over the momenta of the final state particles. And this is the general expression for any two-body decay. Now, the fundamental physics, of course, as usual, is contained into the matrix element, so the transition probability amplitude MFI, okay, which depends on the potential. So this tells you everything about the decay, the physics beyond the decay. And all the additional factors are, again, kinematical factors, which describe the phase space available and also the momentum conservation through this delta function here. Now, let's consider again the non-relativistic transition probability amplitude at first order in perturbation theory. Okay, so what we discussed essentially 1 hour ago. Let's make use of the Born approximation. So we suppose that our initial and final state wave function are just plane waves for simplicity. Okay, let's express the elementary volume in spherical coordinates. So r squared, dr, sin theta, d theta, d phi. And let's express our potential energy in terms of a certain potential U through a coupling constant G0. Okay. Now, this is absolutely general, although, of course, in the Born approximation. Let's now make a special guess for the potential. Okay. So suppose that your potential depends on the distance r in this way. So we have a dependent here on the exponential and also on the denominator. Okay. So the one you see here is a static central potential. Both strength depends only on the distance r. Okay, we don't have any more the dependence on the direction, but only on the distance. Generated by a point-like source of infinite mass. So this infinite mass approximation is just to tell you that we can neglect the recoil, okay, of the source of the potential. Now, capital R denotes the range of the potential, and G that you see here is just an integration constant which is proportional to the intensity of our source. Okay. So under specific circumstances, this potential reduced to the Coulomb potential. So if your constant here, G divided by 4 square, you replace by the electric charge Q, and if you put the range to infinity, then you obtain immediately the Coulomb potential. So essentially, this potential here is a more general central potential, which includes the Coulomb case as a special case. Now, this potential was, as I'm sure you know already, was introduced by Ucava in 1935. This is known as the Ucava potential, where R is given by h bar divided by mc. And this was introduced at the time in the attempt to describe the internuclear forces in terms of exchange of boson. So Ucava already back in 1935 had a very modern view of interactions among particles. At the time, of course, elementary particles were not known, and the people was focused on nuclei, atomic nuclei. And the idea of Ucava is that atomic nuclei interact between themselves through the exchange of some boson, okay, which is essentially the incept of the modern view that we use today in quantum field theory for discussing particle physics and particles and interactions. So, imposing that the range of the nuclear forces, so these are here, is of the order of the size of the atomic nuclei, so of the order of few Fermi, and this was already known at the time. But just inverting this expression of R, okay, he found out that the mass of this hypothetical exchanged boson should be of the order of 100 MeV. And so he made a prediction for the existence of allied bosons with the mass of the order of 100 MeV, with the role of a mediator of the nuclear forces among atomic nuclei. Now, the Ucava particle turned out to be the pion, okay, with a mass of 140 MeV, so slightly above his prediction. And as we will study next, this was discovered in 1947 in cosmic ray showers, after being erroneously exchanged with a slightly lighter muon. So essentially, 10 years before, in 1936, so right after the Yuca Potential theory, a new particle was discovered in cosmic rays with a mass very close to the expectation, 100 MeV, okay? So everybody was happy to have found the Ucava boson, but it took actually 10 or even 11 years to realize that this is nothing to do with the pion. This is a lepton. It's just, let's say, the heavier brother of the electron, okay? And the pion was discovered only in 1947 with a mass slightly higher, okay? We will come back to this anyway later on. So the pi meson was then considered the carrier of the nuclear force that keeps atomic nucleus bound together. Today we know that the pion, of course, is not a fundamental particle. It is a meson, so it is made by quarks and antiquark. And instead, at the fundamental level, we know that the strong interaction is mediated by gluons, as we will study then in the QCD chapter of the course. Let's now, anyway, derive the transition probability amplitude for the Ucava potential. So let me go back now to the blackboard. Okay. So we're going to make a non-relativistic treatment, okay, just based on the perturbation theory and Born approximation. So the first order perturbation theory, we have seen that this is the integral over the complex conjugate final state of function. Then we have our interaction, and then we have the initial state, and it is overall the elementary volume, element of volume, the tau. Now, in the Born approximation, as I was mentioning before, we just consider plane waves for phi I, phi f. So this is integral for e to the minus I over h bar p f scalar r. Then we have our interaction PR. Then we have e to the magnitude I over h bar p I scalar r in the tau. Let's make now more explicit this potential energy in terms of the potential and the coupling constant. So we put the coupling constant outside of the integral, just a constant. Now we have the U R in general, okay? And then this we can merge together as E to the I H bar Pi minus Pf scalar r in the tau. And if we now define the three momentum transfer Q as Pi minus Pf, then we can write this as G0 integral U r e to the I over h bar Q scalar r in the tau. Let's now make use of natural units. So from now on, we will put h bar equal to 1. And this we can rewrite here as Tfi, which is now a function of the transfer momentum Q. So this we can also write as f of Q. And then we have our expression here, where we now can put here the full expression of the Ucava potential. Okay. So this is J0, then we have G divided by 4 pi integral. We have a triple integral because we are integrating over the volume in spherical coordinates. So e to the minus r divided by r divided by small r, e to the I q r cos theta, where we made this scalar product explicit. And then we have the elementary volume, r squared dr sin theta d theta d phi. So let's now decompose the three integrals. So we have 0 g over 4 pi. We first collect the integral over d phi, which is the most trivial because there is no dependence on phi anywhere. Okay. Then we have our integral over r from 0 to infinity, e to the minus r divided by r. And inside here, we solve our integral on theta. So integral from 0 to pi, e to the I q r cos theta in sin theta d theta. All this is nested inside the integral over r, so we still have r squared dr. Now, this integral is known. We will not solve it, but if you find in tables, it is a known integral. So let me just go to the result. So this g0 g over 4 pi. Then we get a 2 pi from this integral over phi. Then we get the integral from 0 to infinity of what remains, minus r over r divided by r. And then the result of this integral, which is trivially twice sine of qr divided by qr, not squared in the r. So we can now simplify a few things. So r squared goes with r here and r there. And then we can simplify the 4 pi. So we have 4 pi with 2 pi and 2. So what we get, what we remain with is g0g integral from 0 to infinity e to the minus r over capital R sine of qr divided by q in the r. Now, let me remember you that in the Ucava theory, capital R is a h bar over mc, and in natural unit, it is just 1 over m. So we also consider C equal 1. Okay. So when we substitute here, we get our f of q is equal to d0 g integral from 0 to infinity e to the minus r m, which comes from here now. And then we make use of the Euler formula. So this is e to the I q r minus e to the minus I q r divided by 2 I q in the r. Here we're using the Euler formula. And again, this is a known integral, okay? This can be solved analytically, and the result is g0 g times 1 over q squared plus m squared. We can also call this pi of q, so we have g0 g pi of q. Ok. Ci siete tutti? Allora, ritorniamo sulla slide adesso. Devo fare lo sharing. Ok, adesso dovreste vedere di nuovo la slide. Ok, so the quantity that we just derived on the blackboard describes in general the probability amplitude for the scattering of a particle, which is coupled to a constant G0. Okay, so a particle momentum pi coupled through a coupling G0 to what? To a static potential generated by a point-like source of infinite mass, so we neglected the recoil of this object here that generates the potential, and intensity G. Okay, so this is the classical interpretation of what we just derived. But now, of course, as I mentioned before, Ucava had a modern interpretation of this same result. Okay, and in the Ucava approach, this quantity here, 1 over q squared plus m squared, is interpreted as the probability amplitude for the exchange of a boson of mass m and momentum q between two interactive fermions. Suppose we have a fermion of mass 1 and a fermion of mass 2. They interact in this view through the exchange of a boson with mass m and momentum q. Okay, and this quantity here is nothing else than the probability amplitude for the exchange of this boson. Okay, so in this view, the boson acts as a mediator of the interaction between two fermions. This is a very modern view that is at the basis of the modern quantum field theory, and also we will study this in detail, of course, through the Feynman approach and the Feynman diagrams at the proper time. Okay, so still in this interpretation, so in the Ucava approach, this quantity here is called the bosonic propagator, and represents the probability amplitude for a mediator boson of mass m and momentum q to propagate from one fermion to the other. Now, what about now the other two objects, the G0 and G? So in this modern view from Ucava, the G0 and G are called vertex factors. We will generalize these when we will deal with the Feynman diagrams, of course. So these are called the vertex factor, and they represent the probability amplitudes for the emission in the upper vertex and the absorption in the lower vertex of the mediator, okay, and describe the coupling of the exchanged boson to the scattered and scattering particles. Okay. Let's consider only, for the moment, only the upper part of the diagram. Okay, so only the part which deals with the emission of the boson. So we have initial fermion that goes into fermion and a boson. Now, an important thing to note here is that this upper part of the diagram violates energy conservation by a certain amount, okay, which is equal to the difference between the initial energy and the final energy. So let's consider the emission process in the center of mass system of a fermion. Okay, so in the center of mass, the total energy of the initial state is the mass of the fermion. Okay, in the final state is given by the center of mass energy of the emitted fermion and the emitted boson. And this we can write in terms of the total energy, so in terms of momenta and mass. And of course, this must be greater than the initial energy, which is just mf, which is just this term here. So you have many more terms in addition to this. So the final energy is greater than the initial energy. So energy conservation is violated at this level. And this is also true in the case of a massless boson. Okay, so suppose now our boson is massless, like for instance a photon. Suppose our process is an electron that goes into electron and gamma. Then the initial energy is the mass of the electron. The final energy is the total energy of the outgoing electron plus the total energy of the photon, which, being massless, is only given by the momentum. Okay. And again, this is greater than the initial energy, because this is greater than just ME, which enters here. So, of course, the radiation of a photon is a real process that happens. So, in reality, the radiation emission from a free electron is possible. However, only where a recoiling nucleus is present in the neighborhood, which absorbs the exciting momentum. And this is the well-known Bremsstrahlung emission that you know. Okay. What about now the lower vertex? We have the same problem, but opposite. Okay, so the violation of energy conservation is opposite in the absorption case, where now our lower fermion absorb the photon. So if you consider the upper part and the lower part separately, you are violating energy conservation. Okay, and so it appears that when you merge the two together, there is indeed a violation of energy conservation, which is, as you know, a fundamental requirement of any physical process. Okay. However, quantum mechanics help us, okay, because the energy violation delta E can only occur in the time interval allowed by the uncertainty principle. So you know from quantum mechanics that you can have an energy conservation violation, although this can happen only in the short time allowed by the uncertainty principle. Okay. You can also now invert these and find that the time where the energy violation is allowed is smaller than h bar divided by delta E. Now, in the time interval delta t, the boson can reach a maximal distance c d tau. So suppose in the best scenario that the boson is massless, so it moves with the speed of light. So the maximal distance that it can cross in a time delta t is just c times delta t. So one can estimate the range of the forces just by this, okay, by using now substituting into Rmax this expression. So Rmax is c delta t, but delta t we can extract from the uncertainty principle, okay? So we have c s bar divided by delta minimal. The minimal value of the energy violation, which gives the maximal of the range, is just the rest mass, mc squared. And so at the end, we just have h bar divided by mc, which is exactly the expression of R from the Ucava theory. Now, a few consideration about this relation. So what we learned here is that since the range of the interaction is inversely proportional to the mass of the exchanged particle, the exchanged boson. Okay. Now, of course, photons are massless. Okay. So this guy here goes to infinity, and in fact, we know that the range of the electromagnetic interaction is infinite. Okay. What about the weak interactions? The weak interaction is very well different, because now the masses of the weak gauge bosons, the Ws and the Z, are very high, order of 100 GeV. So when you put here 100 GeV in the mass, you get a very small range for the weak interaction of the order 10 to the minus 18 meters, as I was telling you in the very first lesson. What about gluons? So gluons are massless, so one would expect a similar behavior than photon. So one would expect a strong interaction with infinite range. However, this is not the case. As I told you in the first lesson, the range of the strong interaction is extremely small, is of the order 1 Fermi. How is this possible? Well, this is due to the intrinsic features of quantum chromodynamics that we will study at the proper time. Okay, and so in particular to the concept of confinement. Now, since the violation of energy conservation occurs within the uncertainty principle, it is not measurable, and therefore it is allowed. Okay. So we have energy violation that occurs in such a short time that is allowed by the uncertainty principle. The net effect at the end is the exchange of energy and momentum between the two fermions. And this is indeed exactly the way fermions interact. Now, there is an alternative and common way to interpret the process, which is the following. So instead, we assume that energy and momentum are conserved at the vertices, but the exchanged particle does not satisfy the relativistic energy-momentum relation. Okay? This is an equivalent way to say the same thing. Okay? And a particle that does not satisfy this relativistic relation for energy momentum is not a real particle. So we can close our circle in this way. So in contrast to real particles, which are called on-mass shell, which satisfy this momentum-energy relation, particles not satisfying this relation are called virtual particles or off-mass shell particles. And so the interaction between fermions then, in this view, in this interpretation, occurs through the exchange of a virtual boson. And this is indeed, this approach is at the basis of the Feynman diagrams that we will be studying in the next weeks. Okay. So today we can stop here if you have questions.
Sorry, can I ask a question, please?
Sure.
I was asking myself, but when we talk about virtual particles, we can say that, for example, a phonon is a virtual particle.
Phonon, okay. Yes, if it does not, yeah, you exchange photon when you have vibrations between atoms and molecules, right? So yes, in the sense that if it does not fulfill this energy momentum relation, yes, it is a virtual particle. So you exchange a photon as a virtual particle. And the virtual particles cannot be detected experimentally. They live only within the experiment, the uncertainty principle, the time given by the uncertainty principle. So they are there, they are exchanged by particle, but they can never be detected.
Okay, okay, perfect. Thanks.
One more curiosity about this relation here. When you have, for instance, an electromagnetic interaction where your exchanged boson is indeed the photon, okay, a virtual photon will not satisfy this relation, and so it may also be interpreted as a massive particle, okay? So a virtual photon can have a non-zero mass because it's not satisfying this relation here. Of course, you will never be able to measure this because it only lives within uncertainty principle. Okay, other questions? Okay, if not, we can stop here and see you tomorrow at 11. I will now stop sharing and registering.